share screen. Yeah. So, okay. Yeah. So today we will start with machine learning, discussion machine learning. Previously we discussed Python and the related package, and NumPy and pandas. So now we will get to the machine learning topics. Okay. And so before we start, so just a quick overview about generally speaking, three different types of machine learning. So the first one is supervised learning. So supervised learning, and later on in our example, we will have better understanding, but right now, just a general idea is, it says the data is labeled. Okay, is a labeled data. And because of its labeled data, then so we will have like, it's a direct feedback. Okay, and what it works is a kind of training on this labeled data. And then if the training model reaches certain level of performance that you think it's acceptable, then you can use the model to predict future outcomes. So that's what a supervised learning. And also in machine learning, generally speaking, when we discuss labeled data, so regarding that we call data set. So for the data set, later on we will also see a lot of math formulas. So it involves like X, like Y, kind of like a math parameter. And then generally speaking, and of course, it's a kind of like vectorized, okay. And generally speaking, like for X, so in math, we know, then it's some variables, okay. And over here, we said it's represent features, okay. And the Y is here, what is the outcome, and we call it targets. Okay, targets, so features and targets. And with label data is the training data. Training data has, so there are a lot of samples. So for each sample, each of its feature in the training data regarding each sample, regarding of the features for the sample, then it has a outcome. So that outcome is already labeled. So the targets is labeled. Okay, so that's what we call as supervised learning. And for supervised learning, so like one kind of application is you can predict like a house price. So here the targeted, so regarding this kind of application, so the data set, the target is the house price. Then what are the features? So features may be like a number of bedrooms, like a square foot, maybe neighborhood, number of garage. So etc. So, and of course, like that modeling, etc. So a number of features. So those are considered features. So generally, they will represent like as X, Y, X value, and then the house price is going to be the Y values. Okay, but the house price, then the idea is you may have tens of thousands house, and you have for each house, you have those features. And on the market, you already know the corresponding house's price, is it? So then you set this to train in the model. And then later on, maybe then you have, so someone may want to know like a specific house price, assume, is it? Then just input with those features, number of bedrooms, square foot, neighborhood or garage, and number of garages, then the model can predict the price. So that's what we call supervised, because when you do the training, the house price, that's the target, is already labeled. Another example is like identify a cat or a dog picture. The cat or dog picture. So then in this case, the training data set contains maybe also tens of thousands of cat, dog pictures. And it's labeled, as if for cat, it's a label cat. And for dog, it's a label dog. And then later on, you can just get a picture to the model for some application. Then the application can tell you it's a cat or dog. So that's what we here said, supervised learning. And for supervised learning, there are generally also consider like one category is classification. So classification, then the class label is discrete. So discrete like a cat, dog, is it? It's not a continuous value. So it's a cat class or dog class. So that's called a classification. Another is a regression. So regression is a continuous value, like the house price. So maybe there are some certain pattern, is it? So that's continuous value. Okay, so that's under supervised learning. So that's the first type of machine learning. Second type is unsupervised learning. Therefore, unsupervised learning, there is no labels. And because no label, and of course, there is no feedback, then it's the model. So you just feed off the raw data. Then the model can find some hidden pattern, hidden structure for us. Okay. And generally speaking is like you can find some subgroup using clustering. Okay, using clustering. So the one idea is like customers. Is it the customer? And some supermarket, so for example, like a Walmart, they collect a lot of customer buying habits. Is it? Then based on the buying habits, then you can group the customer, like maybe the difference between female customer and the male customer, or maybe like kids and seniors. So something like this, because for all of the data, it's just buying habits. Is it you buying more food, or you buying more electronics, or you buy more games? Is it something like that? And then based on that, then you group that, because clearly we can see there is no label. Is it just raw data, just the buying items and the spending the cost, is it? So then based on that, the model can find some pattern and group the data together. Then this using, we call it clustering. Okay, so this kind of unsupervised learning. Or unsupervised learning can also be used for dimensionality reduction. Okay, so remove noise, but won't degrade performance too much. Okay, later on we will see how do we also do dimensionality reduction, so remove some noise. So that's the second category. Okay, the third category is called reinforcement learning. So reinforcement learning is involved decision process, but the decision process also there is some reward system. Okay, so if like to some targets, you move to some targets, and during the process, you are towards the right direction, then you get some rewards. And then so it's through series of actions and you keep getting rewarding. Then because it's rewarding, that's why it's called reinforcement learning. As a reinforce, and so then it's going to reinforce you to take certain actions. So that's what we call reinforcement learning. So generally, we said in the reinforcement learning, there is some system we call some agent. Okay, that's going to improve its performance, but it's based on the rewards. Okay, and one of the example and reinforcement used a lot in games. Okay, and if we may also heard like AlphaGo, that Google's AlphaGo game. So that's use reinforcement learning. And of course, a recent number of years, we also heard a lot about deep learning. But deep learning, it can, so deep learning, there is supervised deep learning, unsupervised reinforcement. So we generally don't like get deep learning as a specific like a type. Okay, and this semester we will also see deep learning. Okay, so that's the general idea about 3 different types of machine learning. And then we will start with 2 simple machine learning, and both of them are supervised. Okay, here. So we will start with supervised, and the simple, we can say it's maybe considered simplest. Okay, supervised learning approaches. Okay, and Perceptron and Adaline, okay, adaptive linear neurons. So this is the kind of like the starting point for later on. We will also learn neural network, the very, very basic concept, okay. And both over here, they are going, supervised learning, if you recall, it can be used for classification. And it can also be used for later on we will also see like regression, so so classification is for discrete, so the data value is not continuous, and the other type is for continuous. And we will see both of this over here. It's used for classification. So it's kind of like a cat or dog. So let's start with the very, very basic, okay, about the artificial neuron concept, okay, the early history of machine learning. And it's called McClock-Pitts, so MCP neuron. So if you see this, they said it's these 2 scientists, Warren McClock and Walter Pitts, they first proposed the concept of the neuron concept. And later on, we will also learn neural network. So basically, this is kind of like the starting point. So this kind of take the idea from biology, the nerve cell, okay? So consider as a neuron. So like in this diagram shows, okay, the nerve cell. So you have input. So like just like human being, you take input. We call here input signal, okay? Input signals. And basically input signals in previously what we learned is all of the features, okay? And what it does, kind of like in biology, humans, neuron is all of the signals coming in, is it, to the nerve cell, then they are going to be integrated into the body, cell body, okay? And then it involves some kind of accumulated. Okay, so we're going to do some accumulation. So the feature is the vector X. Is it? So how do we accumulate? We will see. And then for the accumulated signal, if it exceeds certain threshold, so you define some threshold to determine the output signal. Okay, generated will be passed by the axon. So the output signal basically is our Y. Okay, so that's the target. So that's the, so over here is just a single neuron. Is that? So this is simply the case, okay, and the threshold. So we call it MCP neuron. It's very abstract. Okay, later on we will see the math behind it. And then let's see, artificial neurons, is it? And it says a few years later, another scientist, Frank Rosenblatt, he published the first concept of, we call it perceptron learning. Okay, it's based on MCP neuron model. Okay, so here we have the concept of perceptron. So that's what we are going to learn today first. So perceptron, probably we can call it an algorithm, is it? And the other one is Adaline. Okay, so he proposed the perceptron learning rules. So what is this perceptron learning rules is based on what? It's using some weight coefficients. So if you recall previously, we said it's integrate and augmented signals. So what does that mean? So basically over here, what he proposes to use some weight, because with all of the input, so this is, so it includes a number of features, is it? So all of these are the features, like a number, so this may represent like a number of rooms. Is it? This may be square foot, something, is it? So anyway, so those are the input signals. And how do you establish the relationship with the house price? Is it? And so in math, generally speaking, we can write like it's some function. But here, we don't know what that function, because if you know that function, then we don't need to do training. Is it? So that's hidden. Is it? Because you only have data. Is it? You only have the raw data. So how do we find the hidden pattern? Is it? So over here, the idea is, how do we find the optimal weight coefficient? The weight coefficient. So the weight coefficient, generally speaking, is it? So in math, you know some function. So function means it's regarding. So you have maybe some so some kind of coefficient. Is there some kind of coefficient? You multiply the specific feature. Is it? And then you can find some relationship. So over here, this kind of coefficient, then we call it weight. So weights. Okay, but we don't know, is it? That's why we need a lot of data to train, to find the optimized weight. Okay, and so what we do is you use the weight times the input data, the features, is it, for each one of it. Okay, and then you try to see what this result is going to be. So there is going to be some threshold. And if it's reach the threshold, what should we do or should not do? Is it? So it says multiply with input feature, then to make a decision. Okay, make a decision to decide if we are going to fire the neuron or not. So that means if you're going to get the predicted, get the outcome, is it the target or not, and what the target is it? And there's that. So once you find the optimal weight, then you can, because that means you know this hidden function, is it? Then if you have a new data, a new sample, then you can find the predicted result. So that's the general idea, okay? And of course, over here, because it's just weight times the input features, is it? So this is a linear relationship, okay, linear one. So the idea is kind of, if I draw it visually, and of course, over here, I just assume you only have one feature, is it? And this is the outcome, the target value, is it? So based on what we learned, is it, what we just mentioned, so all these dots are samples. So each of these dots is a sample. And the sample, because it's a sample and this is supervised learning, so it has its X value and the corresponding Y value, is it? So what this perceptron learning is trying to do is it try to find some, because over here we're trying to find the weight, is it, times the X, is it? And try to see how close it getting to the Y value, is it? So maybe through a number of times the training, you find some kind of relationship like this. Okay, so then this slope. So basically this linear, this line slope is our weight. Okay, is our weight. And once you find it, it's and of course it's not perfectly, it is, but it's try to it's maybe getting really close. Okay, so that's the general idea here about the weight. And here is the perceptron concept. And then let's take a look. Okay, so regarding perceptrons, artificial neurons, so here just a single one, okay? And there are a couple of terms we also needed to get clear. The first is called decision function, phi, okay? And here there is another one, we call it net input. What is net input? So here x1, x2, 2, xm, of those we already learned, is it? They are called features. So if we represent, like in math, it should be a vector, is it? And because the goal is to find optimal weights. Okay, what does that optimal weight mean? That means once you find the weight, and whenever you have a future X, and it will very high accuracy, it will predict the result correctly. Okay, that's what we our goal is optimal weights. And the optimal weights, so here we have the features, is it? So our goal is to find the weight vector. Okay, and here we just do linear combination. Okay, so we just multiply weight and the feature value together. And then we add them together. So this, we call it a net input Z. Okay, net input. And then we need to, and if you recall, for neuron, then it's fire or not. This is a neuron. So that means you predict the result correctly or not. So here, this, so you need to make some decision, is it based on this net input? So that's why we call this phi function called decision function. Okay, decision function. So for the decision function in the perceptron algorithm, it's a pretty simple one. Okay, it's going to use what? Unit step function. So this phi is a mass unit step function. So mass unit step function, it's, if you recall, is that it's just so unit step. So it's based on, so if we do some normalization, then it's kind of like if it's greater or equal than 0, is it? If it is, then you go to here. Otherwise, you go to this line, is it? So it's just always either like 1 or -1. So over here, then this theta is the threshold. Threshold. Okay, so for this threshold, if the net input greater or equal than theta, is it greater or equal than theta? Then we say, okay, it's maybe dog. So this is a class 1. And otherwise, it's another class. So it's not that class, is it? Okay, so it's another class 2. And of course, over here, it's just binary. Is it? It is that class or not? Okay. And so here we have a couple of terms. Okay, so keep that in mind. Decision function. So decision function in perceptron, it's just unit step function. And we also have the concept of net input. So net input is just the features times the weights. And our goal is to find the optimal weight. Okay. And in perceptron, the decision function then is a step function, unit step function. So if it's compared with certain threshold, so if net input is greater or equal than threshold, then it's one class, then otherwise the other class. So this is a very basic idea about perceptron. And here, it also involves the formal definition, okay, about our perceptron. And so just keep that in mind, okay, so theta is the threshold, but we can rewrite, is it? Because initially, Z is net input. So net input is sigma xi wi, is it? So I started from 1 to m. So this m is number of features. Okay, feature means number of rooms, number of square foot, number of bathroom, number of garage, those called features. Okay, features. So this is called net input, is it? And previously we said, okay, if this net input greater or equal than theta, is it? So this is threshold, then it's some class, maybe dog, is it? Otherwise it's a cat, is it? So for the binary classification. Okay, and with this in math, you know, is it? We can move this to the left, is it? To the left side. So then it changes to theta, negative theta, is it? Plus sigma wixi, is it? 2m from 1, is it? And of course, for this term, we can change it. We can, because generally, if you recall in math, for linear a linear relationship, is it? So it's ax plus b, is it? You have a slope. You also have interception, is it? This is also a linear one, is it? And over here, we didn't consider the interception. So if you move this to the left, then it's negative. And basically, we can also assume that x0 is 1. Okay, and then this can be considered as the first weight, W0. Is it W0? So we can rewrite like this. Then the net input changes from W0 x0 plus W1 x1 all the way to xi. But remember, feature, these are the features. The first one, x0, it's not a feature, okay? It's always 1, always 1, is it? It's the W0, okay? W0 in this case is our threshold, okay? Then in this case, we can make a decision based on the net input, because later on that's what we are going to do. We always use net input Z, okay? So then here, net input also include x0 and w0, include the threshold. So basically here is that the negative threshold away w0, is it? Normally we call it in machine learning a bias. And the bias later on, we will also say it's very important in training, okay? Bias, variance, okay, regarding performance, we will discuss, okay? So this bias is also very important. And what it is, let's keep that in mind, okay? So in Perceptron, basically it's just that threshold. So this is a formal definition. And then let's take a look, because over here it's regarding classification. Classification, is it? Just like in this diagram shows, as a diagram shows. So here we have two. So here we have two features, x1 and x2. So this is regarding two features. Okay, two features. And with these two features, it may be like number of rooms and the square foot, is it? Something like that, or maybe like for cat and the dog, it's a difference, is it? So their features. So anyway, just two features. Based on these two features and all of this, the red dots and the blue dots, they are all samples. Sample. And we can clearly see these two samples can be divided. They can be divided. So this is one group, and this is another group. Okay, and with this two group, basically it's what? So this separated line, is it? Separated line. So this is net input. Input Z, is it? Net input Z. And this net input Z, and this is vector format. Okay, vector format. Basically it's sigma I from 0 to m w I x I. Okay, so in math you learned. And so this is what? This phi Z is the decision function. Okay, so in this case, if the decision function is 0, then it's a separate line, is it, for the two class? Okay, so if the decision function apply to the sample. If it's greater or equal than 0, then clearly it's on the right side of the separated line. Otherwise, if it's less than 0, it's on the left side of the line. Is it? Then you can clearly see these are in the two different classes. So it can discriminate between two linear separable class. Okay, here be careful, it's linear separable. Okay, separable. And here is a mass expression for the relationship between decision function and the net input. So this is Z, okay, net input. And it's either go to this 1 or go to this -1 as a unit step. Okay, so this is we already see that. Okay, then you may ask, how do we train? Is it? So the question regarding what we just saw, that example, is it? So you have all of those lines, of those samples, and then, so how do we find this line? This is separated line. That is, so if you want to find it, then basically you need to find the weight. Is it? So how do we find the weight? So that's what we call, we are going to use, we call it some learning algorithm. So over here it's called perceptron learning algorithm. Okay, perceptron. And then just think about it. Is it? So because we don't know the weight, but it depends on the weight and the, and I should write like this, okay. So this is equals to I from 0 to M, so Wi, Xi, is it? And so, but we don't know of this weight, so unknown. But we do know this. This is known from samples, is it? From samples. So the data set, training data sets, and we do know those X. Is it? We do know those X. Because we don't know the weight, but we know a lot of those samples. So how do we find this optimal weight? So the perceptron learning, so basically overall in machine learning, the idea is we can initialize the weights to some random small number or 0. So it depends your design. Okay, generally speaking, we pick some very random small number. And for the random small number, and then for each training sample. Okay, so here training sample represent as X, the superscript I. Okay. So for each of the training sample, then here is your tryout weights. Is it? So assumed weights. Then you can, using this net input, is it net input? We can find, then we can find if it's greater or equal than 0 or less than 0, is it? Then you can find it's 1 or -1, is it? And this -1 or -1 is predicted target. Predicted target value. Because what? Because it's based on your assumed weights, not the optimal one, because you assume some very small one. Just try, is it, to see. Try to see if it works. Then you can, based on this weight calculation, then you can determine if it's greater or equal than 0. Then you can make a decision if it's 1 or -1. Is it? And this one, the -1, is not the real one. Is it? So that's why we have the little hat. So this is predicted target value. Okay, predicted target value. And this, and we have the y. Is it? So y is training samples target value. Okay, so this y hat and the y, it may be the same, it may be different. Is it? So maybe it's 1, but your y hat is -1. Then it's different. And maybe it's 1 and your predictor is also 1. Then that matches. Is it? That matches. So here it says the output is a class label predicted as if by that unit. So I already explained. And then based on that, we can update the weights. So we are going to update the weights, okay, for each of the features. Okay, for each of the, so J here represent a feature. Okay, I, the super represent a sample, okay. So we can update. Is it because initially you say, okay, I initial with 0.0. Then after the first sample, I find that there's some discrepancy, so I can update the weights. And so the updating is based on some updated the weight value, is it? And how do we find this delta W? So that's based on the real training target value and the predicted one times the feature. And here there is a lambda. So we apply some small number. This we call it learning rate. So maybe like 0.01 something. Then you can find out the delta W. Is it? And you apply this delta W back to this equation, then you updated the W. And for this updated W, then for next sample, okay. For next sample, then you're going to use this updated weight. So for each one of it, it will go through this. Does it go through? So gradually, so maybe initially your line is here. The separate, then definitely it's not correct. Does it? So with the weight, keep updating, it's getting close. And until the weight is optimal, then you find this perfect optimal separated line. Then you get this two class separated. So this we call it a learning. So learning is also based on the learning rate. So you can set the learning rate. So the learning start with some, so the learning start with assumed weights. Then it's through the learning rate, is it adjust the weight, and you keep updating weight. Okay, and you get your weights getting close and close to the optimal one. And then you can find some of very highly performed separated line. Okay, so that's the idea. Find the separate means you find the optimal weight. Okay, so that's the general idea about perceptron learning. Okay, and for perceptron learning, the rule is it must be linear separable. Okay, only linear. Okay, so it says convergency of the perceptron can only be guaranteed if two classes are linear separable. Okay, and the learning rate is sufficiently small. So that's the condition. Okay, for perceptron learning convergency, because it may just back and forth, and never get to the optimal weight, is it? So that means maybe it's not linear separable, is it? Okay, so must be linear separable. So linear separable, that means you find the optimal weight. You find the optimal weights, then you find the optimal line, is it? The separated line, and then you separate two classes, is it? And here, like this diagram, is not linear separable. And for this one, it's definitely, there is no line, linear line can separate. But later on, we will see, like for this, then we can use some other way to adjust, then it's also separable, okay? And I say if the two classes cannot be separated by linear decision boundary, as I said, you can set some maximum number of passes over the training data set. Okay, we call it epochs. Okay, because you will not be able to let it do the training forever. Is it? So if reach a certain number of iteration, you can still not get optimal performance, then we should stop, converge. And or is that some threshold for the tolerated misclassification, because you cannot expect 100% correct. As you may say, okay, maybe 95% correct, then I think it's pretty good. So that's regarding perceptrons learning rules. And the next one is regarding Adaline. Okay, so it's called adaptive linear neurons. For the adaptive linear neuron, and we will see it's also called batch gradient descent algorithm. Okay, and this is going to be the over here. It's kind of the foundation work for more advanced machine learning algorithms for classification, like logistic regression, support vector regression model. Okay, so it's kind of like the ground one, the gradient descent, including like a neural network. That it's all using the concept of gradient descent, and it's a very nice concept. Okay, and here, and for gradient descent, here for the Adaline, we call it batch gradient descent. So batch gradient descent consider all samples together. Okay, all samples together to do the training. And there is another one later on, we will also say it's called stochastic gradient descent. Okay, and then in that case, it's sample by sample. Okay, so online or offline, a lot of time we call that. Okay, so anyway, so here we will get to know the idea about gradient descent. Okay, a very nice idea. And the key difference between Adaline and the perceptron is, for perceptron, the decision function, and sometimes we also call activation function, it's a unit step function in perceptron. So in Adaline, we are going to change that. Okay, So in Adaline, we are going, so the decision function, activation function, we are going to use a linear activation function. Okay, linear activation function. And in this case, this linear activation function is just the net input, the identity function of net input. So that's our activation function, okay? So just also keep this word term in mind, activation function. So in this case, for Adaline, it's just the net input. And I think I kind of run out of time. So